Very good morning and welcome back to the second session of fourth day program. We have with us Professor Vivek from TIFR. Now I request Dr. Devaprada Sarkar, Research Assistant Professor, Department of Physics and Nanotechnology, to introduce the speaker and chair this session. Over to you, Debu.
Thank you, Cynthia. So it's my pleasure to introduce Dr. Vivek Polshettiwar. So he is Associate Professor in the Division of Chemical Science and TIFR. So Vivek did his PhD from DRDO, Gwalior, India. Then he moved to France to work as assistant as a postdoctoral research at EM. So Vivek's research has taken him to Europe, US, and Middle East also. So during this time of abroad, he was awarded as a prestigious uh, ORISC research fellowship to work at US Environment Protection Agency. So in 2013, he moved to TIFR and his group were working on the development of novel nanomaterial for catalysis, energy harvesting, and CO2 capture in conversation. So he also owns several awards, including top 25 cited author in 2011, Young Scientist Award at DLS DSL 2012. He also received Asian Rising Star Leadership at 15th ACCC, Singapore. And in 2015, he is Fellow of Royal Society of Chemistry, UK. So his innovation is very well known in this field who know Vivek's research because of his innovation on the dendrite fibers nanosilica, KCC1. So welcome you, Vivek, in our SRM IST. So now I request Dr. Vivek to start this talk.
Okay, thank you. Thank you very much, Dr. Devabrata, for your nice introduction. And thank you very much, Dr. Navinithan, for the invitation and giving me the opportunity to present the work. So this is more like a refresher course. So you guys can stop me at any time during the talk, and maybe we can go in a discussion mode rather than I'm talking and you guys are listening, because I know there are several excellent scientists are here. SRM is one of the best private university. I visited once the chemistry department and it was amazing. So I think we can have a nice discussion rather than just a talk. So let me share the screen. Okay. So today I'm going to speak about the work that we do in our lab, where we make different kinds of nanomaterials and try to tune their catalytic properties by tuning the obviously the size, shape, morphology, the defects in the material, the interface if you are using a hybrid nanomaterial. And I'm going to discuss these results and explain you how these can help us in terms of sustainable environment and energy to combat the climate change ideally. So so my content of this talk will be I will introduce, or I will discuss in brief the dendritic fibrous nanosilica, DFNS. Then I will explain how one can create the defects in these nanosilicas, and then that allows us to prepare metal-free catalyst. Then I will explain the dendritic plasmonic colloidosomes, black gold, how to synthesize them and why they are black, and how one can use this black gold to harvest the solar energy and then transform the photon or use those photons to generate hot electrons and heat, which can again be used for catalysis. And at the end, I will try to touch upon our recent work where we prepared very acidic aluminosilicates, acidity very close to zeolites, but still they are amorphous and mesoporous. We call it as amorphous zeolite. So objective of our group is to contribute against fighting the climate change, to come up with a solution to contribute in combating the climate change. So if one look at the climate change issue, this one slide explains our life, our daily life, right? So the trees and plants take these energy from sun, they harvest the sun energy, and they use the CO2 in the environment, water, and CO2 plus water, we get lots of foods and different chemicals also. Somehow we have produced lots of CO2 in the environment, industries, because of the industrialization and the way we live our life now, more artificial than natural. So we produce too much of CO2 that any number of trees that you plant, they will never able to take care of the CO2. Even the ocean is already acidified and warming because of the excess amount of CO2. Obviously, we should plant as many trees as we can, but we know that is not alone is going to solve our problem. So what one can do, what chemist can do, or what material scientist can do to take care of the CO2 problem, which is ideally a climate change problem. Because if I'm able to, capture the CO2 and convert into useful chemicals and fuels, then CO2 is no more your problem, right? It could be your source of carbon. So how do I make CO2 source for carbon rather than a source of a climate change? So ideally we have to develop something which trees does, harvest solar energy, capture CO2, split water, react CO2 plus with water and get you the food products. Similarly, can one design artificial trees which will do the same thing, harvest solar energy, activate CO2 and give you the different chemicals and fuels? So this is where I'm going to show you. So artificial trees are again a fancy word, fancy name, just to attract. But ideally, these are the nanomaterials, catalytic nanomaterial, which will have the ability to harvest the solar energy and then convert or use those solar photon to produce the hot electrons or a heat, and you can use those for carrying out your reaction. At the same time, the artificial tree has ability to capture the CO2, but CO2 is a linear molecule, sp hybridized, extremely stable, extremely unreactive. So to make them unreactive, CO2 has to be chemisorbed on the surface. So artificial trees, which is nothing but a nanocatalyst, are not only harvesting the solar energy, but they should also be able to capture the CO2 and chemisorb them and bend them so that they are reactive. And third thing that the artificial trees has to do is again take the water, capture the water, split the water again into proton. I need that proton, I need hot electrons or excited electrons and the activated CO2 to get you the product methane. So if that is possible, then one day we may be able to run our car by CO2. This sounds very excessive, but look at the chemistry. I fill a car with a CO2. In the car, I have this catalytic reactor, which has the ability to convert CO2 to methane or a methanol, both are fuel. Methane is nothing but a CNG, so we are already running our car using methane. CNG is 99% methane. So if that catalyst can convert CO2 to methane using the sunlight, then you see CO2 goes into your car, catalytic reactor convert that into methane. Methane is your fuel, burn the fuel, you get the energy, you drive your car. Same thing can be done with different engines and bikes and everything. Car is just an example of doing the function. And once you burn it, you get the energy that you do a function, drive the car or something else. And you get a CO2 which you don't let go out in the environment, but then again recycle back to the catalytic reactor and get the methane, right? This is called the cyclic economy, where CO2 is not releasing in the environment, but CO2 has become the fuel actually by using catalytic reactor. So maybe I will show you some examples how this is possible. This is absolutely possible. Obviously, right now that is possible only at a lab scale with a very minimum productivity. But science is there. It's only about the breakthrough in the fundamental research in the field of a catalysis or nanomaterial synthesis, where if one can develop a catalyst which will really take lots of CO2 and produce lots of methane at extremely high kinetics, then this is possible. You can drive your car with CO2. So today I'm going to show you how one can develop these catalytic reactor, these catalyst systems, which can convert CO2 into methane or methanol. So This is how we do it in our lab. It's some sort of a 3-component system. The 2 components are support and active site. So support, so we need artificial trees are nothing but nanocatalysts, and you need these nanocatalysts, nanomaterial, to capture and convert CO2. So to do that, you need a surface where CO2 get adsorbed and can be absorbed. We call them a support. You also need an active site which will then catalyze the reaction of CO2 with hydrogen or CO2 with water. And you also need energy to drive that reaction towards the product direction, right? So there we're trying to use solar energy to drive the reaction by converting those solar photon into either hot electrons, electron hole pair or excited electrons, as well as the heat. And you can use them separately or combine these hot electrons and heat to carry out this reaction of CO2 plus hydrogen coming from water splitting or by itself. And this could be separate step, or this could be in a combined step. And then you get a methane or a methanol. So I will go one by one. I will explain you about the support, active sites, and then solar to and the energy. So use of solar energy to carry out this reaction. So support. So as the name suggests, support should be a material which should have very high surface area so that lots of CO2 can get absorbed. Even you can load lots of active site and still it has enough surface area so that CO2 can also absorb and then diffuse towards the active site. However, if you look at the literature, there are lots of high surface area material. Most of them are because of the porosity, right? So if you look at a metal organic framework, they have very huge surface area, but most of them are a microporous material, pores with a small, less than 2 nanometer size. So the accessibility of those surface area is difficult, right? There is a diffusion issue. Even with a mesoporous material like MCM41, SBA15, these are the name for these porous silica material. Although they show excellent surface area because we measure the surface area using small nitrogen molecule, but when you do a catalysis in reality, what happens is as soon as you coat these surfaces with the active site, which is my next step, you start blocking the pores. So I'm ideally using very small portion of the surface area and remaining portion is not accessible. And then the reactant has to reach each of these active sites, which is also challenging. So we thought of developing a material which would also have a high surface area, but not due to the pores, but due to something else. For example, due to the spikes or fibers. And you can see now these are external surface area. So it's easily accessible. Even I quote the catalyst, you can see catalyst is also on the external part of the surface. So they are also easily accessible. So this is what we developed in our lab. We call it as a dendritic fibrous nanosilica, DFNS. So these are the nanosilicas having a dendritic fibrous morphology. That's why the name DFNS. So one can have a, can everyone mute please, so that we will have no disturbance. So one can have a particle size from 50 to 100 nanometer, 100 to 200 nanometer, up to 1.2 micron size. So based on the application, for a drug delivery, you need a smaller particles. For other application, you need a bigger particles. We can also tune the surface area. Okay, so there is a question which I like to answer before I move forward, where it is Dr. Jashandeep Singh says, sir, is BET a reliable technique for surface area measurement? That is the best technique. Why you say it is not reliable? It's one of the best technique that you have. For one of my sample, I did BET 3 times and 3 times I got a different surface area. So there is an issue with your instrument or operator. Hello. Sorry. Okay, so I think the BET is the.
Please everyone mute. Please everyone.
Can I request everyone to mute yourself? I hope they are listening. Anyway, so the question is whether BET is a reliable technique. It is a reliable technique and it is the best technique available. It has its own limitation, but we'll not go into that. But it is one of the best technique right now. Okay, so this is our material where we have a silica with a nanoparticle from 50 to 100 and 1200 nanometer, high surface area 500 to 1200 meters per gram. excellent thermal stability and mechanical stability. So one can use this for, high temperature and high pressure reaction. And most important thing, we haven't used any fancy technique. It's easy to make. We even use, if you go to this nature protocol, we have explained step by step every single step so that you can make it in your lab. And this doesn't need anything. It's a round bottom glass and heater and magnetic stirrer. That's it. We even gave the video how to make them. So I think if you are looking for a material of such a type, you can easily make it even at a larger scale. So these are the SEM images indicating that they are monodisperse spheres. When I say fibers, they are not like a hairy fibers, but they are more like a petals of the flower. And at the nanoscale, they look like a fiber. So that's why we use the word fibers. These are the TEM images, again indicating the fibrous nature. And it looks like there is a solid core in here, but there is no solid core. It's more dense fibers at the center. That's why the electron transmission is weak. And that's why they are darker, this contrast difference. You see a pore surface area is around 600 in this case with a very good pore volume. And the uniqueness is the pore size distribution. So when I say pore size, ideally these are the distance between the two fibers, right, this way. So when I move from center to the periphery of the sphere, you can see now the distances are increasing. And that's what you see here. You have around 45 angstrom, and then that's around 5 nanometer, and then you have pores up to 25 nanometer. So this allows you to even have bigger molecule to diffuse in. And if you want to do a catalysis with a bigger molecule, that can also be used. There's a question by Dr. Ashok Behera. Are they porous? Yes, that's what I'm saying. They are a porous material. That's why, otherwise you cannot have such a high surface area, right? So these are all porous material. But definition of porosity here is different. Generally, pores are closed, tubular or random pores where you have one entry and one outlet. Here, these are the fibers open from all the sides. So they are porous, but then those pores are accessible from all the sides, which has its own advantage and disadvantage. Okay. Yes, they are porous. That means we can enter the drug inside it for sustained release drug information. Again, another question by Dr. Ashok Behera. Yes, you can, and I will show you that the people have already used it for lots of drug delivery applications. Yeah. So before that, I will explain to you. The question that we ask in our lab is why these spheres are dendritic fibers. Why not a solid sphere or a hollow sphere or some other shape, other morphology? Why this particular? And that's the question that we ask in our lab. The formation mechanism of this material, and this is synthesized using the technique called the templated synthesis, where you use this type of organic molecule as a template. You can see there is a quaternary nitrogen, which is a polar head shown as a blue ball, and you have this CS2 up to 16 times, which is hydrophobic tail. So you have this polar head and hydrophobic tail. These are the surfactant molecules. And we know whenever we add the surfactant molecule in the solution, in the solvent, they try to form the micelles, reverse micelles, standard micelles, or sometimes lamellar phases. You see, they were self-assembled to form such a lamellar phases. And I will show you the animation for a more clear version. So these are the template molecules, polar head, non-polar tail. We added them into a solvent. Here it's the water and xylene mixture, and to minimize the total energy of the system, because there's lots of repulsion if they are randomly oriented. So they try to self-assemble and orient properly so that they will have a minimum repulsion. They form these lamellar phases, but there are still a repulsion between this quaternary nitrogen. So we added one more co-surfactant, pentanol, having this OH polar group, and they stabilizes these interfaces. What we observe is these lamellar phases are not flat floating in the solvent, but they are in the form of a droplet. They're in the form of a microemulsion droplets. And these droplets are the reactor. These droplets are the template made up of just water, xylene, and the CTAB. Now you can grow your silica in these channels that you see. So by tuning the size of this droplet, I can tune the size of the DFNS. We can keep these droplets away from each other. You get a smaller particle, or I can merge them together and you get a bigger particle. We can also tune the thickness of each silica fibers, each silica sheets by changing the channel depth or channel width. So that's what we learned, that we can tune the sizes from 50 nanometer to 1200 nanometer at different ranges. We can also have a one sphere with a different number of fibers. That means if the fibers are less, they will go away from each other. If fiber density is more, they will come together with each other. And you can tune the pore size distribution by that. Right, so this material is used worldwide now. This is our invented and patented material, which is used by 150 groups worldwide, not only for catalysis and CO2 mitigation, but the question asked about the drug delivery. So lots of work about drug delivery, but you can imagine they are porous, having a tunable porosity. So you can use load the drug and selectively release. They were also used in sensors, energy storage like batteries and supercapacitor, and energy harvesting, which is ideally part of the catalysis. Okay, see some questions there. Yes, Dr. Jashandeep Singh asked another question. Morphology plays a role in this role. As you use the template method, so final sample is a template free or it contains some residue of the template? No, so template, the meaning of template is that, right, that you remove the template. So it should be template free. I haven't explained you the synthesis, but once the DFNS is formed, you can remove the template, which is CTAB, organic molecule, by simply burning it. So if you heat at 550 degrees Celsius in air, they will go away and you get a very pure silica. If you don't want to heat, you can do a solvent extraction by ethanol or something, and you can take out all the template. So that is possible. What effect of the size for synthesis of a nano range for this DFNS? Dr. Ashok Behra asked. I don't understand the question, but what if you are asking that how do we tune the size? Then I already told you that we tune the size by tuning different reaction parameters, the co-surfactant. We keep the template droplets away from each other, so they are very small. You get a small particle, we merge them to get a. Another question, Jashandeep Singh, nano rods or spheres, which will be better? That is very, that's not a question, right? Because it depends on what is the application, right? It could be sphere, it could be nano rods. So based on what you want to do, one has to find out which one is better. So that cannot be so general, saying, oh, nano rod is better or sphere is better. Yes, I can share my preference and patents. Okay, I will now take the question afterwards. So that's the first part where I showed you the catalyst support. The second part is the active site, because these are the silica materials, SiO2 with some OH on the surface. So they are not that catalytically active. So we need to ideally put some active sites so that they can catalyze these CO2 reactions, CO2 reduction reaction. So we also wanted to put then some active site. So if you look at the literature, the best active site is the metal nanoparticles. This is one of the best example by Bert Wilkinson, where they use nickel nanoparticles supported on silica for CO2 hydrogenation to get you methane. But the problem with metal nanoparticles are they are reactive, but they're also very unstable, because the nickel 0 can oxidize to say nickel 2 or 3 or plus 1. And because of these oxidation, nickel is no more active. And these nanoparticles then also undergo some sort of a sintering, and the particle size grows. So that will also reduces the catalytic activity, and within a few hours the catalyst dies. So we wanted to solve this problem. Now if I replace the nickel by any other metal, it will have the same issue, right? Most of the metals are very reactive, but they are also unstable because of the oxidation and sintering. So we thought of, can one replace the metal by no metal? Can one do a metal-free catalysis of the CO2 activation? So then how do I do it? Then we propose this hypothesis that, can I create a defects in my material which will activate the CO2 and which will dissociate the hydrogen? How do I create the defect? See, this is the silica. I'm showing just the surface of the silica. This is amorphous. So SiO, 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 it's a random network of siloxanes. If I break these SiO bond here, I will get O radicals and Si radicals. If I break both the bond, I will get a 2 Si radicals, something like this. I get an O radical and Si radical. This is called NBOSC, non-breaching oxygen hole center, because you broke the breach. And then Si radicals are called E center. These are just the names, but ideally it's Si radicals and O radicals. And if you break both the SiO bond, then you get these oxygen vacuums shown here. So we asked two questions. Can I really generate these free radicals? Are the defect sites in the material? and whether they will activate the CO2 and dissociate the hydrogen. So two questions that we ask. So how do I break these bonds selectively? So, and this is our work that we recently showed, where we showed that yes, one can use these defect site. One can create and use a defect site for CO2. I will explain why, how. So there is this very old paper by Rao et al. In 1976, before my birth. So they published a paper where they said, okay, if you take a SiO2 and magnesium vapors, magnesium, see it in a tube, seal it, no air, no oxygen, and heat. As soon as you heat at 75 degrees Celsius, magnesium now has lots of vapors in the reactor, and magnesium needs the oxygen. Since there is no oxygen in the environment, magnesium takes the oxygen from the SiO2, and that's how it is. That's like it breaks one bond first and then another bond, and then magnesium becomes some sort of magnesium oxide, and SiO2 start losing its oxygen. We thought this can be selectively used, right? Rao et al. And then there is a follow-up paper in Nature, Bao et al. So there they converted SiO2 to Si for using this magnesiothermic treatment. We said, okay, let us stop at reaction step 1 by tuning, the magnesium concentration, reaction time. And by tuning that, we could stop and tune the number of Si radicals and O radicals, and that may give us a catalyst. So we tune the weight of magnesium, 10 weight percent, 25 and 50, and prepare a range of these defected DFNs. So this is a normal preliminary characterization indicating that the morphologies remain nearly intact. Maybe at higher loading there is some loss, and surface area is also okay. Maybe at higher loading again with higher concentration of magnesium, the surface area reduced to 100, but still it is not a bad surface area. This is a typical imaging, normal light and UV light indicating that there could be a defect sites which are emitting different wavelength of the light. To get a real picture, because this is just a qualitative, we did the photoluminescence study, and we observed that pure DFNS you have this defect around 420, 430 nanometer, which is for dioxysilane and silylenes. But when you treat them with a magnesium at higher temperature, that particular defect concentration vanishes, and you create new defect sites around 810 nanometer, which is for that O radicals, the NBOSC site. And you can see DNS25 has the highest, no, DNS10 has the highest amount of these defect sites. To see the E centers, the SI radical, we did the EPR, and using the EPR, we observed that the E center concentration increases from 10% to 25 to 50%. So with these characterization, we went ahead and say, let us see whether they can be catalytically active. And we tested these reactions, CO2 plus methane, CO2 plus hydrogen, to get you methane plus water, and there is something missing which is plus CO, carbon monoxide, it is written here. So you take CO2, you take hydrogen, mix them, and then this is your catalytic reactor. You have the catalyst here, which is heated at 400 degrees Celsius, 1 bar. You pass the gas, and then you monitor by the online GC. Monitor the product formation, methane, CO, and water. Water you don't monitor, but you get it in other reactor. So methane and CO ideally. And this is a catalytic results. So you see now DFNS, no defects. When I say no defects, all the materials always have some defects. Right? It's really difficult to get a defect-free materials. But those natural defects are low in concentration. But with 10, 25, 50% Mg, we increase those defect concentration, created a new defects. And you can see now, because the methane yield is around 3750 micromole per gram per hour with the DFNS 25. With more increase in the defect concentration, the yield goes down. We will ask that question, that why 25 is better. And we also show that it's stable, the catalyst is stable, but not 100%. You started with 4000 and ended with 3000 micromole per gram per hour in around 24 hours. So we thought, since there is no metal nanoparticle, there cannot be oxidation, there cannot be a sintering. So we thought this could be because of the carbon formation, right? They can form a carbon, some sort of a non-oxidative CO2 degradation, CO2 reduction. So our hypothesis was this decreasing because of the carbon formation. So we burn the catalyst. We heated that in the air to remove the carbon, And what we observe, every time we regenerate, the catalytic activity keep increasing up to say around 7 to 8 cycles, and then they are nearly same in the error bar. But if it is just a carbon which is stopping the reducing the catalytic activity, then why will it increase every time I regenerate? That means it is not because of the carbon, it must be because of something else. So I will try to explain that part also. So the first question is why 25 is better? Because DNS10 has highest number of O radicals, NBOSE side, and DNS50 has highest number of E centers, SI radicals. Still, the catalyst which is best is 25, DNS25, neither 10, neither 50. What this indicates? This indicates that these two sites are working cooperatively. You need to have these two sites nearby in the proximity, and they need to work together. Then only you are getting the good catalytic activity. That's what it indicates, and I will show you some results indicating the same thing. And this particular data, which I will skip to save the time, explains that every time you regenerate, you are producing more and more defect sites, and that's why you keep getting more and more catalytic activity. Yeah, so then we did this in situ diffuse reflectance measurement to understand which defect sites are interacting with CO2, which defect sites are interacting with hydrogen, so that we know who is activating CO2, who is dissociating hydrogen. And based on this data, which again I'm skipping, not going into more technical details, we came up with this proposed mechanism where we showed that the O radicals and the silanols activates the CO2 like this. And then here, the SI radicals here, the E centers is the one which dissociates the hydrogen. See here, SI interact with hydrogen with the help of this precarbonyl, which is coming from the CO2. And then you see now it is dissociated. That bond is broken. You get SiH, and that H is gone to the carbonyl, and you form this pre-formyl type of molecule, intermediate. And you keep adding another hydrogen molecule, and once you add these 4 hydrogen molecules, you get a methane, and this SiH containing material, which you heat, and you again create these Si radicals and O radicals, or oxygen radicals. Right. So I will not go into the details, but this is how we propose the mechanism, which indicates that you need a proximity of the two defect centers. Okay, so that was the second part where I showed you the active site can be something other than metals. Now, if one has to look at the drawback of that process that I just explained to you, is it needed 400 degrees Celsius to carry out that CO2 methanation, which could be the reason for non-sustainability of such a process. So now the question is, can I get that energy from the sun energy? So because solar energy is freely available, so if I can manage to do that reaction using the solar energy, it should work. But that is a thermal reaction. No, it's not a photocatalysis, it's a thermal catalysis. So how do I convert the solar photon, or how do I use the solar photon to get that heat? One could be just focusing that solar light by some lenses, but that will be uncontrolled heating up to 1000 degrees Celsius, and it will kill your catalyst. We need to have a controlled heating. In another case, this is a new term, new concept you can say. It's not a new concept, it's a new word, cold heating. What I mean to say here is, when I do a catalysis, and when I'm saying that catalysis is happening at a 400 degrees Celsius, you need that 400 degrees Celsius only at the active site where you have to overcome the activation energy. Ideally, I don't need to heat entire reactor if I can manage to get a 400 degrees Celsius at the active site. So your reactor can be cold or a room temperature, but your active site can be at a 400 degrees Celsius. Can something like that be done? And yes, the nanoscience has improved like anything. It's like magical thing, where you can use the concept of surface plasmon resonance, SPR, to achieve this. We know the gold is shiny yellow color. Why? Because this is a metallic, it has electron cloud on the surface, so it reflects most of the light photons, except near the blue region, some very small portion, and that's why I get the yellow color. Whereas when I change the bulk gold into smaller nanoparticles, you start getting different colors. But it indicates that the electron cloud on these metal nanoparticles start resonate with the wavelength of the light, start oscillate with the wavelength of light. And at one particular wavelength, there is a resonance between the electric component of the light and the electron cloud. These oscillating electron cloud are the free electrons, and then that energy get absorbed, and when these SPR get damped, that energy then get converted into either the heat, the loss is by the thermal energy, or that energy then excite the electron in the Fermi level, and then the electron goes to the excited state. We call them energetic electrons or hot electrons. Now one can use these hot electrons in the gold, transfer them to a CO2 to get a CO2 radical anion, and those are a very active species to react with. Or one can use the heat that is produced to carry out the thermal catalysis. And so that's what we wanted to use. Only problem with these system is, if I take a silica and load it with the gold nanoparticle, the light absorption is like this, the blue curve, around 550 nanometer. But if you really want to have a sustainable process with a very good yield, then you need to prepare a material which should absorb entire visible and even a near IR light, something like that, a broadband light absorption. How do I achieve that? How do I achieve a broadband light absorption? So there are two ways one can tune the light absorption behavior of these gold particle. One is by simply changing the size. But you see now when I move from 9 nanometer to 20 to 48 to 99, what is happening? The lambda max is changing. It's not becoming a broad, but shifting from one wavelength to another because of the size in the electron cloud. Another way, which is called the interparticle distances, where if you bring the gold particle near to each other, the electron cloud of gold particles start interacting with each other, and then that entire electron cloud start resonate, start oscillating with the light and have a different resonance wavelength. It's called the plasmonic coupling. So we thought of using these two concepts and see whether even here you do not get the broadband light. But we thought, can I combine these two and see whether I can get a broadband light absorption? So that's what we did. We tuned the distances between the gold particles from D. You can see D is decreasing by skip this, by the cycle by cycle approach, where C0, C1, C3, C4, C6, you see the gold particles are coming together, and also there is a heterogeneity in the particle size. This is the TEM images. These are the TEM images indicating that when I go from one cycle to another cycle, particles are coming closer to each other. Even in C6, they started connecting. Even C4, some portions are connected. We don't want them to connect. We want them to keep away from each other because my reaction is happening between the gaps of the gold nanoparticles. If they are connected, there is no gap, and then you cannot do a catalysis. Surface area will be low, or volume will be low. So skip this one. Yeah. So you can see now the light absorption behavior. When you only have a gold nanoparticle supported on silica, they like this. They are like brown color or the light red color. But with more and more cycles, that means when I bring the gold particle nearer and nearer, you start seeing a black gold, physically a black gold, a material which is gold but black. And believe me, this is a gold is in a zero oxidation state. It's a metallic zero oxidized gold, no functionalization, no doping, nothing. Still it is black, and because of that interparticle plasmonic coupling, and also the role of a particle size heterogeneity. And you can see now this one, which was absorbing only around 550, now start absorbing more light in the other part of the visible spectrum, and it becomes broad. So what is the advantage? It's not just because of the color, but that color, black color, is because it absorbs all the light, and then that light energy get damped to produce heat, thermal heat, or the hot electrons. And that thermal heat can be used for catalysis. And this is a side reaction that we did, where we showed that one can also convert seawater into drinkable water. You take a seawater, put the black gold, expose with light. Black gold absorbs that visible light, solar light, and produces lots of heat. And then that heat will evaporate the water. You condense the water, and you get a pure water. We observe that C4 is the best material because it heats very fast, so around 7-8 minutes. We also wanted to know the temperature of the surface. See, this says it can heat up to 90 degrees Celsius, but this is not a temperature of the gold surface, because once the heat goes from gold to water cannot boil above 100 degrees Celsius. That's one question. But then there is a heat loss from water to the environment, right? So this is not the way to see the surface. So how do I measure the surface of the gold nanoparticles? You cannot use a thermometer, right? Because you are a nanoscale. This is a very nice technique called the Raman thermometry, where you use the ratio of Stokes and anti-Stokes lines. If you look at here, we know that if you are heating a molecule, then they are in a higher vibrational states. So the population in higher vibrational states will be more, and you should get more anti-Stokes lines compared to the Stokes lines. And that will be directly related to the temperature of the surface. So this is the formula where if you get the ratio of anti-Stokes versus Stokes line intensity, then all of these are constant and you get a T, temperature T. So by using this, we calculated the temperature, measure the temperature, and we observe that one can go up to 150 degrees Celsius by simply exposing with light. Now you will say that the previous reaction that I was doing was at a 400 degrees Celsius, and the temperature I'm getting here is 150. So ideally, I cannot use this system. It's true, but there is something else that is happening here, which doesn't happen in a normal thermal catalysis, which is the surface plasma not only has the heat, but it also has this polarizing electric field. So when your reactants are in the polarizing electric field, they try to bend themselves to dissipate the extra energy that they got, maybe because of the electron transfer, permanent electron transfer, or a transient electron transfer. So when they go to the excited state, some sort of a hybrid state between the gold and the molecule, and when they go to the excited state, there these molecules bend, the bond angle changes, bond length changes, and that becomes really reactive. So now, since they are reactive, the activation energy required for these CO2 adsorb on the gold surface will be less. That means I need a lower temperature to carry out that reaction, what I was carrying at 400 degrees Celsius. Okay, it's already 50 minutes, 40 minutes. I have another 10, 15 minutes, I guess. So I will.
Yes, Vivek, you can continue 10, 15 minutes.
Okay, another 10 minutes, Devabata?
Yes, 10 minutes.
Okay. So I will try to finish in 10 minutes, and then we can go to the QA session. So we also try to, so in addition to the thermal hotspot, there is also the electromagnetic hotspot, and we also wanted to know which material has the better, more electromagnetic hotspots. For that, we did this SERS, surface enhanced Raman spectroscopy, and we observed that C4 again has the highest number of electromagnetic hotspots. We also try to visualize these hotspots by these electron energy loss spectroscopy yields, and we see that when the gold particles are going closer and closer, you see now the brightness indicates the energy of hotspot and the intensity of those hotspots. So it's more in the C4. Whereas as soon as you have here, you have more gold particles, but they started connecting with each other. So you see now the brightness decrease because now they have no gaps between. They are connected with each other. So you need gaps to have a hotspot. So that's what we saw in the yield studies. So all our studies show that C4 is the best material. So we took the C4 and did some catalysis. So this is a simple catalysis where alcohol oxidizes to aldehyde, and there is a side reaction of forming the ester. So if alcohol to aldehyde, you see the conversion. Take a C4. In dark, it is around 20%. In light, it is around 90%. You can say, oh, this may be just because of the difference in the temperature. No, temperature was maintained at the same temperature. The reaction temperature was the same, by using this water circulator. So if it is not the temperature, what could it be? Then the hypothesis was that when you expose the black gold with a light, you excite the electron in the Fermi level to higher state, energetic electrons or hot electrons, and these hot electrons then get transferred to the oxygen. Oxygen is your oxidizing agent, and you dissociate the oxygen. And now you have a dissociated oxygen, which is highly reactive, and therefore you get a better kinetics of the alcohol oxidation. Now, how do I prove this hypothesis? How do I prove that there is electron transfer from black gold to the oxygen and oxygen is dissociating? For that, we did this particular experiment, hot electrons instead of dissociation. So if I add more and more photons, more and more intense light onto the black gold, I should produce more and more hot electrons, and these more hot electrons will produce more dissociated oxygen, and that should increase the rate of a reaction. That's what we did. We put more and more light, 0.4 watt per centimeter square, 0.5, 0.6, and you see the rate of a reaction increases in a superlinear fashion, indicating that yes, it is because of the hot electron transfer to the oxygen from the black gold. So that's a very unique mechanism that happens only in the plasmonic catalysis, not in other thermal catalysis. So we also tried the CO2 conversion, CO2 plus water to get you the methane. You know, I told you this, that you can drive your car by filling the CO2. Looks very excessive, sounds very excessive, but look, CO2 plus water, black gold, light, which is a solar light, I get a methane. You burn the methane, drive the car, and again, don't let CO2 go out, capture it, send it back to the catalytic reactor, a cyclic process, and it works. Only problem now is the y-axis. Methane yield is 1.5 micromole per gram, which is too low. Still, it is best in the literature. If you just take a gold, it's a 10 times less. So our black gold material shows far better activity. But in real application, these are very small numbers. You may need to increase this to say 1500 micromole per gram per hour, something like that. Very fast kinetics. Then one can achieve this state. So there is a science. One has to come up with a better catalytic design. You may also think that, oh, why should I use a gold, which is expensive? True, but it is catalytic. Once you have it, it should be usable for large number of cycles. And gold are known for their stability. We are also trying to replace gold by some other materials, but it's not that easy. Okay, in next 5 minutes, I will quickly explain the last part, which is a nanomaterials for waste plastic to chemicals. In addition to the climate change, waste plastic is a serious issue, and it's more serious in our country where we are unorganized, throw everything everywhere, and it is lying everywhere. It is not only on the land, but it is also in the air. The microplastic is in the air. There is very recent science paper where they showed that when there was a rain, they call this is a new acid rain, plastic rain. Plastic is coming into our water system, and then you eat the plastic. We are already eating plastic. I don't know what will happen after a few years. So plastic is another very serious issue, which we try to ignore, not taking much steps. But what science can do, science or the chemistry part, or material scientists can do, is take that waste plastic and go back to the chemicals from where it was made, right? You degrade the plastic into the basic chemicals. The chemistry is known, you just heat them and you can degrade them back, but then you need a very high temperature, high energy. So you don't want to spend a 5 rupees plastic bottle to claim back, you don't want to spend 20 rupees on it, right? So energetically, it's non-sustainable. But can we make it sustainable? Can I degrade these plastic bottle at a lower temperature using some catalyst and make this process sustainable? And that's what we recently showed, that we prepared a solid acid whose acidity is as strong as like a zeolite, but zeolite is microporous material, issue with the diffusion, whereas this is a mesoporous material, bigger pores and pore size distribution. So we came up with a new solid acid which has a porosity like aluminosilicates, amorphous aluminosilicate, but acidity like zeolites. And combine these two factors, we showed that one can degrade the plastic, even the CO2 reduction to dimethyl ether. So we use again the DFNS protocol to make this material, but we replace some of the TOS starting material by the aluminum ACAC, and we make sure that they condense together to get you the zeolitic type bonds, which make it strongly acidic. And these are the normal characterization like SEM. It looks like a sponges with a good surface area 588 and very high pore volume for such a material, 1.3 centimeter cube per gram. And we showed range of different reactions like this particular catalytic reaction. You can see ZSM5, the zeolite, is one of the best solid acid, but it don't convert because it's very small pores, whereas ours is a 62% yield. Another zeolite that is reported in the literature was a mesoporous zeolite. So ours is very close or even better than the mesoporous zeolite. We tried different other reactions to show how good our catalyst is in terms of acidity and the kinetics. Acidity because of the zeolitic type acidic site, and kinetics because of the porosity of the material. I skip all of these, and we also use solid NMR to again show that there is this proton signal at 2.8 ppm, which is known for the zeolitic type silanols, bridging silanols, but we observe that in an amorphous material, indicating this is some sort of a hybrid amorphous aluminosilicate zeolite type material. And here we showed the plastic degradation. So plastic, the one, say take any of example, this plastic carry bag degrade around 550 or 500 degrees Celsius. So we reduce that by 100 degrees Celsius. And you can now degrade that to say 100 or 150, around 350 degrees Celsius. So 150 degrees Celsius less. So you will see total energy required for degradation will be low. But again, can I directly go and use it in the commercial aspect? No, that I have to reduce that again back to say around 100 degrees Celsius. If I can degrade the plastic at 100 degrees Celsius, then this could be a breakthrough. And this is again can be done. We know the science now when we're trying to do this by tuning the surface properties of the material, not only the size surface area, but also the interfaces, how the SiO aluminum is bonded, bond distance. That will allow you to tune the acidity. And if I get even more stronger acidic material, keeping the porosity the same, we may be able to decrease that to even lower temperature. We also showed the use of this for CO2 to fuel conversion, where the catalyst is copper, zinc, aluminum. But once you form the methanol, you have to convert methanol into DME. You cannot use methanol as a fuel, right? So you have to convert into DME, which is a gas. So I don't know why people go for the methanol DME. I feel methane is far better solution. Anyway, if you produce the methanol, we can convert that to DME with 80% selectivity using these amorphous zeolite. Right, so I think I'm on the time, just 1 minute left. So I conclude that I showed you the dendritic fibrous nanosilica, which can be used as a catalyst support, but also for drug delivery and several other applications. And I also showed you how one can create the defects in these material and produce this metal-free catalyst. We use the word perfecting and perfection. That means ideally we say defect is a always think we see it in a negative way, but one can perfect these defects by using their concentration, proximity to make them active catalytically. We also showed that one can tune the interparticle distances between the gold particle to get you the black gold, which absorb visible to near IR light. And then that black gold can be used to harvest the photon from the sunlight and produce the heat only at a specific point of the surface, keeping entire thing cold. And then I also showed you in the last few minutes that one can tune the morphology and the interfaces between the silica and aluminum to get you a very strong solid acid, which is this fancy name of amorphous zeolite, which has acidity like amorphous zeolites and porosity like amorphous aluminosilicate. So ideally, these are amorphous aluminosilicates and not zeolite because they are amorphous. With that, I like to thank my group, Ayan, Rajesh, Rishi, Sushma, another Sushma. I like to thank Department of Energy, which fund us 99% time. Everything is coming from DAE. I also got some external project by Indo-French CETIFRA, Shell Industries, and the STDBT Mission Innovation. With that, I like to thank you very much for listening to me, and I will be more than happy to take the questions.
Thank you, Vivek. And now the session is open for the questions. So, audience, if you have any question, please raise or unmute your mic or raise your hand, or you can drop some question in chat box also.
Yes, I see some question in the chat box. Maybe I can read and answer. Srinivasan, so thank you for insightful talk. My question with respect to retention of a surface area even after catalytic cycling and thermal cycling. You have showed very high surface area of these materials. What about the surface area of catalyst after catalyst recycling? So obviously the surface area I showed you is about the DFNS alone. If you load the catalyst, you will definitely reduce the surface area, right? But that's okay, right? Why you want is high surface area. First is you want to load the active site, and after active site loading, you still want some surface area so that reactant can diffuse in. So even after loading, you keep the surface area, a good amount of surface area. This is very general question. So based on the catalyst, like if you look at the defected silica with a 25 or 10 weight % magnesium, we had around 400 meters per gram surface area. Started with 600, you reach 400. But still, it is a good surface area. So nothing happens during the catalysis. One of the reason nothing happens is the DFNS has very thick silica fibers. They are around 10 to 15 nanometer. So they don't degrade or collapse when you heat them. Whereas if you look at the SB15 or MCM41, they have very thin walls. And when you heat them, they collapse. And the pore structure collapses, and that's why the surface area there decreases, which is not the case in our material. Dr. Jagadish, now the session is open for, okay, no, this is just asking people to ask the question. Simon, how you manage to attach the gold nanoparticle on the tip of a fiber, not on the pores, which may result in the surface reduction? How did you optimize the temperature needed for the catalyst with respect to intensity of light and gold nanoparticles? Oh, several questions. So gold nanoparticles will attach to the surface, right? When I say pore, it's an empty volume. So how come the gold will go into the pore? They will always sit onto the surface, and they are not only on the tip, they are everywhere. They are everywhere, and there is a reduction in the pore volume. There is a reduction in the surface area because you are putting gold onto the surfaces. So, but even after that reduction, there is a good catalytic activity. See, it is just impossible that you start with material having some surface area and you load something and you still maintain the surface area. That will never happen. You will always 100% time reduce the surface area. Question is how much surface area you can reduce, whether that is enough for your further catalysis, right? If I take again the example of MCM, then the surface area dramatically reduced, because if I put a gold nanoparticle on the mouth, then even there is a surface inside, you are not able to access it. In our case, it's open structure. So even I put a gold nanoparticle here, this surface is open. Even I put a gold nanoparticle here, I can access this surface area from other side. That's why the surface area reduction is less. There's always a reduction, but it's less, and it's enough for catalysis. How did you optimize the temperature needed for the catalysis with respect to intensity of the light and gold nanoparticles? Here we did not optimize the temperature. We optimized the light and the wavelength, right? Because you can optimize the wavelength by looking at the light absorption behavior of that, UV visible spectra of that nanoparticles. We know that it can absorb from 550 to around 900. So you can take any light with that wavelength. We generally use entire broadband xenon lamp, which is like a simulated solar spectrum. And then you can play with the intensity. You change the intensity and see which one is the best for you. That's how you optimize the wavelength and the light. For a thermal catalysis, like defected catalysis, again, you carry out a reaction at a different temperature and see which one has a better productivity, better kinetics. And that's how you optimize the temperature of the reaction. Yes, those are the only questions I see.
So one more question is came in the chat box. So this is Simon. So how you manage to attack the gold nanoparticle?
I already answered that, right?
Okay,
just
okay.
for the one I answered. Yeah.
Okay, that is the last one. Yes. Yeah. So audience, do you have any more questions?
Can we use this material for water splitting? Which material? If you're only looking at a DFNS, it's a insulating silica, very huge band gap. So you cannot use DFNS for water splitting. But the work that I haven't showed you is we coated the DFNS with the TiO2, and you had a very high surface area TiO2 material, which can be used for water splitting. Black gold, there are some references for water splitting, but there is some debate whether you can really split water using the black gold. But the semiconducting material like TiO2 coated on the DFNS can be used to split the water.
So thank you, Vivek, for your nice talk. So really, I have enjoyed a lot because I am a follower. So whenever Vivek publish some article, I will follow and check. So he is so much active on Facebook. Just 2 days back, so I also was attended the chemistry of
chemistry in ancient India. Yeah, that is more exciting to me also.
Yes, because all program is organized and managed everything by Vivek. So thank you, Vivek, for your progress and how you developed your field quickly. So it's really amazing. So thank you. And I just have a small question, like as you told that it's important two things. First, chemi absorbs of CO2, and second, not only the chemi absorb, because everyone we know the CO2 is the linear chain. So it is so much it's difficult to convert CH4. So if the linearity it breaks somehow, then it's more active to conversation. Yes. So,
yes.
So did you found any interesting result like because of your active side that it's bending or something?
That part is already studied very well by people using the in-situ IR, where they showed that whenever CO2 can absorb, the angle bends, right? So we have already taken that knowledge and moving to the next step. because that need a very high end in situ and IR techniques, right, to see the bending. But we haven't done by ourselves. But there are lots of nice literature about the change in the angle and the
Yes,
bond length.
there are
And
many theoretical also, theoretical paper I have noticed.
yeah,
Nice.
theoretical as well as the in situ IR studies. I will try to find out and I will send it to you.
Mhm. And thank you for your black gold. That's it's so much interesting because of this hot
Yes,
electron.
yeah, this seems to be
Yes,
an
and so I like the measure her surface temperature measurement from the stroke and anti-strokes from the Raman stroke.
Yeah, that's very unique technique. In fact,
Yes,
when we
so I
discovered the material, we faced this problem, Developers, that how do I measure the surface temperature? You cannot. We at one point we said, oh, it's not possible. Then we came across this. This is very recent paper in ACS Nano or something, where they come up with this Raman thermometry, which seems to be the only the best technique to know the surface temperature of the nanoparticle.
actually recently last 2 years in my lab we are developing this black catalyst so that can absorb NIR part also. So that's why
Uh-huh.
actually yes I will go through for a paper the how you are calculating this. It's very nice. Maybe later I
Uh-huh.
will discuss also.
Yes, yes.
Okay. Okay.
Sure,
Thank you Vivek for
sure.
today's talk.
Okay. Okay. Thank you very much, Navinitan.
Thank you,
So,
sir. Thank you very much for kind acceptance, and it was very informative and excellent talk. Thank you once again. I hope to see you again for many talks in our SRM. Thank
exactly.
you.
Yes, because I remember in 2017 we meet in SRM. Yes, Vivek.
I came once. I came once.
2017 I mean,
You SRM,
SL
yeah.
Pin 2 all together we discussed that time in our auditorium.
Auditorium, yes, I can.
Yeah.
He came. Yeah.
Yeah. There was another big conference. I remember.
Yes.
Yes, we'll be happy again to see you
Yes.
here.
Yes. Once COVID goes away, we will meet
Yes,
again.
yes.
Okay. Thank you, sir. Thank
Thank
you
you.
very much. And Sarkar, thank you very much for sharing this session. And let me join to thanks Professor Vivek Polshettiwar and Sarkar for this wonderful session. And thank you once again. Thanks, sir.